Hi, Chris Kuzmo here. So I made a video which had a lot of mistakes and pauses in it, which we may not actually publish. In it, I made a mistake that's also illustrative and important, and that is I corrected the compute force method when I was using the compute X force method. And the problem here is, in part, an underlying source of the problem is the computations that happen in compute force are virtually identical to the computations that happen inside of compute X force. And so in order to fix a broken computation, and both of the computations are broken, I have to fix it in two different places. It's a classic example of a weakness in your design causing there to be failures in your in an inability or a difficulty in making corrections to your code. And so you'll notice here I put a dot mass times b dot mass as something that before that had been just -1. And there's a slightly different implementation for compute X force where I encapsulated the notion of the force magnitude. The good news there is that I can replace the one here with a dot mass times b dot mass. And that looks like it'll probably be happy now. And you can see that my test passed, but that was because I changed what I was invoking to be compute force, and then I changed it back to compute X force again. So now when I run this, hopefully it will run without an error. It does. It passes 4 and it fails 0. But the key here is in terms of the formulation of the problem, we first discovered that the mass of the mass of each particle, neither of the masses were used in the force computation. And so if you look at the force formula, F equals G, which is 1 for us in our code, uh, times M1 times M2 over R squared, we were not computing M1 and M2. We were assuming they were 1 as well, actually. And so to fix it, we needed to actually put in A dot mass times B dot mass. Now, perhaps at some later point, we will need to introduce G as well, but for now, we're just leaving that as 1. So the good news is that that does fix our problem. And so now if we look at our test case, we say that our test at distance 1 is 4. That's because the masses of the two objects are 2 by default, which is a little bit worrisome, but we'll leave it alone for now. And so now finally we're in a position where we can think about a more interesting test case. But just what we've done right now is enough to give us some confidence that our force computations are reasonable. So that's a great start. We'll want to vary the distance to verify that the distance is in fact being varying inversely square in an inverse squared way. We'll want to vary the masses, and even had we not discovered our error with respect to mass, by varying the masses, we would have discovered that we weren't using them. And then we want to make sure that we can then we want to start operating in testing for 2 dimensions by doing an offset of 3 in the x direction and 4 in the y direction, which will produce an overall distance of 5. And those are nice clean numbers, and that'll make it relatively easy for us to do the force computation when things are not offset in just 1 dimension. So we'll do that, all of those things in the next videos.